All right, welcome everyone. So in this video, we are now going to change focus a little bit from computing probabilities where our area of interest in the support set was a rectangle. So that is what we did in the last video. And we're going to change now to a more general region, which is defined here as D of the XY plane. These problems are a little bit more complicated. I'll confess that they're okay. Yeah, I'll confess that they're not my favorite type of problem. Um, but I do like the amount of logic that goes into thinking how we're going to find these various probabilities. And so, as usual, we'll jump straight into this example. It's the same density that we used in the last video for xy, where x is between 0 and 1, y is between 0 and 1. Again, we're going to start by sketching the support. And I'm going to do this a little bit, I guess a little bit more carefully than I did in the previous video. And so really thinking about sketching the support where x is between 0 and 1, y is between 0 and 1. This is one where you could kind of just do it instantly, but what you're really doing is thinking about taking these inequalities and sketching a line for x equals 0, sketching a line for x equals 1, sketching a line for y equals 0, sketching a line for y equals 1. And so I'll do those in that same order. So x equals 0 is here. The line x equals 1 is here. Y equals 0 is over here. And then y equals 1 would be up here. And so you're sketching those four lines, and then you're figuring out, all right, I've sketched these bounds. Now, where is their positive density? And there's positive density anywhere in this rectangle that I have just sketched. So that strategy will come in handy with the next example when we sketch the support set. Now that that's all sketched out, we're interested in finding the probability that y is less than or equal to x, which is less than or equal to 0.6. And I'm going to use this exact same strategy that I just did, where now the bounds are a little bit harder to sketch. They're still not too bad, but it takes a little bit more work. And so I'm going to sketch a line for y equals x. That's my first inequality there. And then I'm going to sketch a line for x equals 0.6. That is my second inequality in this probability statement. So line for y equals x, that's just a diagonal line here. A line for x equals 0.6, that is something like that. And then I just have to figure out what region needs to be shaded in. And so I know that I want x to be less than 0.6, so I'm shading something to the left of this dotted line. I also know that I want x to be greater than or equal to y. And this is the part where for some reason my brain just has trouble thinking about this. And so what I really like to do is pick a point. So I'm going to pick this point here. So x is maybe 0.4, y is a little tiny bit over 0, and ask myself, is that a part of this inequality that we're trying to sketch out? It is, because 0.4 is bigger than like 0.001, and so I know that that is then the region that I want to be shading in. Okay, now that we've sketched that out, we need to set up our double integral. And you can do this either by integrating with respect to x first or by integrating with respect to y first. And so we're going to do this first by integrating with respect to x first. Okay, so I'm integrating with respect to x first. That means that in my picture, going from left to right, my lower bound is always going to be y. So I'm not always starting at 0 because the area that I've shaded is in a rectangle. And so the lower bound, if I'm integrating with respect to x first, is y. My upper bound is 0.6. So my lower bound's y, then going from left to right, I'm always stopping at 0.6. Then, once I've integrated with respect to x, essentially the x dimension is gone because I've already integrated out x. And so one way that you could think about this, I'll use a different color, is that once I've integrated with respect to x, all of this gets collapsed into just the y dimension. And so then when I'm integrating with respect to y, I'm going to start at 0, and I'm going to go up to the point where that stops collapsing, which in this case is 0.6 again. Okay, so we will, I'm going to fix my drawing a little bit and unshade. 0.6. And we'll again use ChatGPT to figure this out, but before I hop over, we could have also done this by integrating with respect to y first. And so what that is going to look like is instead of starting from left to right, I'm starting from bottom to top. And so if I'm thinking about integrating with respect to y first, y always starts at 0, and then it will always end when y is equal to x. A similar type thing will then happen. So once we've integrated out y, we could think about that as this all just being collapsed into one dimension onto the x-axis. And so then when we integrate with respect to x, our lower bound going from left to right is going to be 0, and our upper bound is again going to be 0.6. So again, once we integrate out y, this collapses into one dimension, and then we're just left with going from 0 to 0.6. Again, I'll fix my drawing. And if we set both of these up correctly, they should give us the same exact answer. And so hopping over to ChatGPT, I did the first integral, and so you could see my prompt here. I said integrate 4xy from y to 0.6 with respect to x, and then from 0 to 0.6 with respect to y. I'll scroll through all this work. Thank God we don't have to do all of that. So I'm not really that old myself, but even when I took probability, we had to do all of this by hand, which of course was a pain. And I'm just going to scroll down to ChatGPT's answer, which is 0.0648. Okay, so that is one example. We're going to do one more. And for our second example, what's going to make this a little bit different is that you'll notice that the support set is no longer rectangular. And so this is actually going to make this even more complicated than the previous example. But it's still not too bad if you break it down step by step. So we're going to start by sketching our support. And remember, the support, it does not show the actual density. So you could think of that as being like a third dimension coming out of the page, but it's too hard to sketch, so we can't actually sketch the density itself. I'm going to use the strategy that I did on the previous page, and so I'm going to, for this support set, sketch the line x equals 0. I'm going to sketch the line x equals y, and I'm going to sketch the line y equals 1, and then figure out where in that little region actually has positive density. So x equals 0, that's here. Y equals 1, that's there. And then x equals y is just going to be this diagonal line here. Again, I like to pick a point in this just to verify that I'm thinking about this support set as being the right region. And so I might pick a point like 0 for x, 0.5 for y, and just verify that those numbers satisfy the inequalities given in the support set, so I know that my support is this upper left triangle. Okay. Then we need to figure out the probability that y is bigger than 0.2. And so I'm going to sketch in a different color the line y equals 0.2. And what we're really trying to integrate over is this shaded region. Again, the density is kind of like popping out of the page, so we don't actually see it, but we're finding the volume under that joint density. Okay. And here, it does matter. Not for the final answer, but for how easy this is going to be. It matters whether you choose to integrate with respect to x first or with respect to y first. And in this case, it's easier to integrate with respect to x first. We'll see why in a moment. But if we integrate with respect to x first, I'm going to take out my highlighter. So I'm starting at 0. So I'm going left to right, starting at 0. And then I'm ending when x is equal to y. And so those are the bounds for my first integral, 0 to y. Again, once I integrate out x, you could think of that all being collapsed into one dimension. And so all of this is just now on this little y dimension that I'm shading here. And that gives us the bounds of our second integral, just thinking about y going from 0.2 up to 1. Again, you could throw that into ChatGPT, which I did, and I'm not going to go back there, but it's a similar prompt to what was given before. And you wind up with a probability of 0.896. Now, we're going to suppose that we integrate with respect to y first. And take a second to think about why this is going to be more challenging. So the reason it's going to be more challenging is that going from bottom to top, it depends on where x is, what the lower bound of my integral is going to be. If my x is between 0 and 0.2, then my lower bound is just going to be 0.2. But if my x is between 0.2 and 1, then my lower bound is going to be x. And so what ends up happening for this is that we need two different integrals to compute this, to address that issue. And so in the first integral, when I'm integrating over y, my bounds are going to go from 0.2 up to 1. And that gives this first part that I'm circling over now. But in my second one, my bounds are going to go from x up to 1. And so again, it has to be different because it has to change depending on where we are on the x-axis when we're integrating out y. Once we do that, so once we integrate over y, then we're thinking about going from left to right. For the first one, x is going to go from 0 to 0.2. And for the second one, x is going to go from 0.2 to 1. And if you do all of this, you should wind up with the same exact answer. So it doesn't matter for the final answer, the order that you choose, but it does matter in terms of work and in terms of, I think, how complex the problem becomes. And I would advise you to think about whether there's an order that only gives you one integral, because that is almost always easier to think through. Okay, all fun stuff. Hopefully this brings back fond memories from Calc 3. Again, I'll say I think this is one of the harder topics, especially in the back half of this course, and so we will get more practice in class, and right away you will get more practice with your class prep quiz.